And welcome back to 13.1. We're dealing with the nature of gases, and in the first podcast of this unit, we talked about the kinetic molecular theory and gave you the points that describe why things behave the way they do. And now we want to introduce you to the idea of gas pressure. It's one of the four parameters that are used to describe a gas, but oftentimes it's one of the least understood, at least at the high school level. And so the first thing you should know is that gas pressure results from the collision of particles on container walls. Now that would be an internal pressure. In fact, you can just cut this thing off if you want to right here and just say that it results from the collision of particles. So for example, when you have a pressure being applied to anything, let's just say we have a person standing on the ground, there's a pressure being applied to this person from the atmosphere. The collision of the atmosphere particles are pressing in on you, the individual. And in fact, in order for you to balance this pressure, your body actually has to press outward. And that balance of pressure in your body actually takes place in your ears. So put little ears on this guy. Here you go. If you've ever noticed when you're going up in an airplane, if you've ever gone up in an airplane, sometimes people's ears will start to hurt. The reason why is your body is pushing out on the atmosphere. What happens is as you go up in an airplane, there's fewer particles above you. Let me try to redraw this thing. Alright, if I'm standing here on the ground, and I'm going to draw it as a little tiny person, if you're on ground level as opposed to up in an airplane, here's our airplane, here's the wing, and I'm going to be standing on top of the airplane, you have the entire weight of the atmosphere pressing down on you when you're on the ground. However, when you're up in an airplane, you only have a little bit of the atmosphere pressing down on you. So as you go higher and higher in an airplane, you have less and less pressure where your body has to press out less and less. But it takes a few minutes to do that. So as you're going up in an airplane, your body is still pressing outward. So if I'm here and in the airplane, my body is pressing out like this, but there's only a little bit of pressure pushing down on us, so your ears start to hurt because it's pressing out too hard, and eventually your body figures it out. And again, that takes place in your ears, actually in a little canal between your jaw and your ears. And that's why, in fact, they tell people to chew gum. If you chew gum as you're going up in an airplane, it helps your body to figure that, it moves that canal around, it helps your body to figure out its pressure, the proper pressure, a little bit easier. The opposite is true when you're going down in a swimming pool. If we're in a swimming pool, here's our swimming pool over here, and here's the shallow end, then it goes down into the deep end, and there you go, there's the wall of the pool. If you are swimming, and as you go down towards the bottom of the pool, you have more and more water pressing down on you. Well, that pressure starts to push in on your ears, and your body's going to have to eventually start to figure out how to get rid of that pressure. How to push back on that pressure. So what will happen is your body is going to push out and try to push back on that water. Now, one way that it does that is by pumping in gases into your bloodstream, and those gases into the bloodstream help to keep your blood vessels open. But what can actually happen is as you come back up, the water's pushing down less and less, but your body is going to have to press out less and less. If you come up too quickly, your body doesn't press out less and less quick enough, and in fact, you can suffer from what's called the bends. Now, in Chapter 14, we'll talk a little bit more about what causes the bends, but in fact, it is a problem with your body trying to change the internal pressure as it's pushing out. Now, gas pressure can be measured with a barometer. A barometer, and you've probably heard of one of these devices before. They are used all the time in the weather. Here's what a barometer is. All a barometer is, in theory, excuse me. Again, all a barometer is a pool of mercury with a tube of mercury inverted in it. And so what's going to happen is this tube of mercury, the mercury is going to want to leave the tube and fill the pan. But in order for this thing to fill the pan, the mercury level in the pan is going to have to rise as this mercury leaves the tube. Well, that wouldn't be a problem except for the fact that the atmosphere is pushing down on this pool of mercury. So in order for this to rise, it's going to have to push against the pressure from the atmosphere. Now, sometimes it can do that, and then the mercury level is going to rise in this in the pool, but the mercury will be able to push its way down the tube. Other times, the pressure from the atmosphere is going to be higher, and it's actually going to push down on this pan of mercury, and it's going to force more mercury into this tube, and it's going to go higher and higher. So you can actually measure the pressure of, say, the atmosphere by using this device. And you can measure the height of this mercury column in millimeters. And you can say, well, the atmosphere has so much pressure because it's suspending a certain volume or a certain height, of mercury. When the atmosphere has higher pressure, it's going to force the mercury higher in this tube. When the atmosphere has lower pressure, the mercury is going to push its way out to some extent, and this level is going to drop. On average, when you're at sea level, we're talking at sea level here, the atmosphere can suspend 760 millimeters of mercury. That's on average when you're at sea level. When, say, you're on the top of Mount Everest, it can only suspend 253 millimeters of mercury. Why is that? Well, because if you're standing, and let's draw another picture. Here we are at sea level. And go up to the top of Mount Everest. There's our mountain. Here I am on top of Mount Everest. When you're at sea level, you have the entire atmosphere pushing down and all around you. And so there's a lot of pressure pushing down, but when you're on top of Mount Everest, there's much less atmosphere pushing down on you. So it's going to be able to suspend much less of the column. That's the basic idea behind the barometer measuring atmospheric pressure. All right. Now, as we scroll down here, and let's try to scroll down. There we go. There are some common units of pressure. First of all, we just talked about millimeters of mercury. Hopefully, you understand why millimeters of mercury can measure pressure. It deals with the height of this column in these tubes that the atmosphere can suspend. As it turns out, 760 millimeters of mercury, which is the average pressure at sea level, is going to be equal to what we call 1 atmosphere, or ATM. It's called 1 atmosphere because, in fact, you have one entire atmosphere pressing down on you at sea level. Some other common units would be pascals. 1 atmosphere and 760 millimeters of mercury is the same as 101,325 pascals. We're not going to show you how we derive that. It's actually derived using physics. Or if you use your prefixes, you can say it's 101.325 kilopascals. And all of these also equal, I believe it's 14.7 pounds per square inch, which we're not going to use in this class, but it's a very common unit of pressure here in the United States. I don't know if they even use that anywhere else in the world. So hopefully this gives you an idea on what pressure is. All pressure is the force caused by the collision of gas particles. You can measure it in terms of the atmosphere anyway, using a barometer, and here are some of the common units of pressure. In the next podcast, scrolling down, we're going to be looking at kinetic energy and temperature.